Mhm. Cool. Probably there. I think music's volume's good. I hope so. Cool. Okay, so let's just get rid of the banner now. Let's double check that everything's working. Should be. Let's see. Cool. Cool. Yep, that's me. That's my other account. Let me double check that everything's working, and yep, that should be it. Yep, cool. Cool, 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 cool. Okay. Hello, hey 404. Long time no see. Saw you with Way last time. You definitely had cool paths from one of the from wiki. What was it? The wiki races, wiki something. I think it was that. Was pretty fun. Cool. Okay, so we'll be wiki races. Yeah, that was it. Thank you. Nice. Okay, so let me just open my OneNote once again. I probably should present my whole screen just because I'm going to be. There we go. Yeah, that should be it. Can you see my screen? Nope. Yes. If I do this, yes. Cool. Okay. So, hey, man. Cool. Okay. Okay. Nice. So, quick refresh. So, thank you 404. It's visible. Quick refresh of what we saw last time, which was on Monday about ROS. Okay. So, pretty quick. ROS is robotics operating system. Okay, so this is what we can see this line, but this is what lots of engineers use for controlling robots. Okay, it's really easy. Using Python and C++, you can control any types of robots as long as they're ROS compatible. Okay, the good thing about this is that ROS is open source. Okay, simple. So you can go and look for robots manuals, and if they're ROS compatible, it's great. If they're not, I'm pretty sure someone has written the drivers for that, or that someone could be you. Okay, either way, it's really fun and really easy to use. Okay, one of the questions that, or like typical questions we get before we start, or like when we actually work with ROS is or are companies using ROS for their products? Yes and no. Okay, so I know for a fact that some of the companies do use ROS as it is. One of them is iRobot, the one that created Roomba. Okay, the robot cleaner. I'm pretty sure they use ROS. Some other companies use a different version of ROS that they change some things. Okay, so it's kind of the same idea, but their way of working with ROS. Okay, just because it's open source and they don't like open source because they get all of the code from there and you can just clone the whole company. Okay, cool. Okay, so that's ROS. Quick overview again. We have a master node. Okay, we can't do anything without that master node, just because in ROS 1 everything goes by the master node. Okay, if in ROS 2 there is no master node, but we're not going to go into detail with ROS 2. Okay, so for now let's just stay with ROS 1. Okay, cool. Nice. I think that was it for last time. Let's kick off from there. Okay, let's start with another. Let's see, there we go. Cool. Another topic. Now we have something called control systems. Okay, so control systems is basically a way of controlling plants or systems based on feedback. Okay, based on the error, math itself tunes itself for it to work. Okay, so let me just put an example here. Okay, so let's say we have a drone again. Okay, 3 and 4. Okay, yeah, that's good. 2, 3, 4. I'm not a good drawer, but hey, it's still a drone though. Let me just do probably this. Okay, and this drone's a little bit happy. Cool. Okay, So we have a drone, and let's say that we want this drone to go from point A, okay, to point B. Okay, so fairly simple, right? Like you'd say, okay, there is, I don't know, 100 meters from A to B. Let's just calculate the time, accelerate the drone, and making it stop at 3 seconds. And with its speed, then it should work, right? And it technically would. Like if you do that approach, which is like the brute force approach, then you go all the way up to B in a fairly simple way. It's not that easy in real life. Okay, real life has wind. So if you say, okay, cool, I want to go from point A to point B, and I want to do it, let's say automatically, autonomously, without using AI, then I would lose a control system. Because if not, if I just go straight forward, it could happen that I could do this. Because you have a wind factor, maybe your controller, the controller of the drone is not tuned up. Okay, so hello. So yeah, you can lose. Let's say you cannot trust in theoretical scenarios when it comes to robots. Okay, just because it can be really dangerous and really expensive. Okay, simple as that. So if you say, okay, it should go straight forward for 3 seconds and then stop, that's a good solution. That's brute force solution. The answer is let's use control systems. Okay, cool. So you may ask, Bully, like, how can I draw a control system? Well, let's draw it. It's fairly simple. We have two types, okay? We have open and we have closed, okay? By the way, we're going to program, just bear with me, because if we go straight to programming, you'll be lost, okay? You won't understand anything, okay? So bear with me with this. We have an input, okay? Let's say input, okay? That goes into something called a plant. A plant is whatever you want to control. In this case, could be a drone, okay? It's going to be one of the robots from our simulation. That's your plant, okay? And from the plant, it just goes out as an output, okay? This is an open loop system because it doesn't have a loop. It doesn't really have a feedback. So this doesn't exist, okay? For this types of systems, it's basically go forward up until like 3 seconds and then just stop. That's not bad, not good either, okay? So let's kind of see what or how closed loop control systems are or look like, okay? We can have, I'll put it, yeah, let's scroll down a bit. Let's put it here. Yeah, there we go, cool. Okay, so we can have, this is closed loop, okay? Let's just write this down. Closed loop. Okay, so closed loop looks like this. We have something called a reference, okay? From the reference, we have something that will be added to it, okay? Then we have the control, which the control will be, let's say blue. That's a weird C. Yeah, I know. And from there, we go to the plant. And from there, we go to, in this case, because we're working with robots. Oh, shoot. Let's see. How can I do this? There we go. Probably should zoom out a bit. Whew. Let's see. Control minus. Yeah, go there. From the plant, we have the robot position, okay? Okay, fairly simple. Robot position. Now, where's the feedback? Oh, it's here. So if we do this, we're adding, by the way, from here goes the error. Cool. So we are adding our position, we're feeding it back into the loop so that it tunes itself. Okay? There are lots of types of control algorithms. What we'll be using is called a PID. Okay? And I'll go in a bit to what that stands for, but I just want to make sure that we have some more words here. The reference, okay, so this one here, the reference, I probably should scroll down a bit, there we go, is basically start to finish. Okay, so I'll just show it here. Start to finish. That's basically the reference. We know that we have to get from point A to point B. That's as simple as that. Okay. And the error, okay, just keep in mind this one, because when we program, we have to write lots of errors, okay? It's the difference between the reference and the robot position. Robot position. Okay, I know it's a lot, but just bear with me, okay? Cool. Again, reference is the distance that we have to go from point A to point B, okay? And the error is between our reference, which is written horribly. It's a horrible F. Shoot. Just rewrite this F. There you go. And the robot position, okay? We can get errors from there. From there, we just feed it back to the loop. Control will do its magic. The plant will act to what the control says, and the robot will change its position. Okay, as simple as that. So cool. So how does this look like? Like, okay, this is too much. Let's just see what we actually want to see in errors. So let's say we have time here, and this is error. Okay. Let's see. There you go. It's a horrible E, and the error usually starts like this. The end should look like this, okay? So that's what we want to see. It's the error go down, okay? Because if not, let's say that you say, hey, robot, just go, I don't know, go from this point to another point, and, you know, I don't know, it could be from point A to point B like this, and there's like, I don't know, a wall here, and it has sensors. So if we don't tune the PID correctly, it will just do this. It will never go into B just because it's not tuned as it should, okay? That's what it will do. It will oscillate, okay? And that in a graph looks like this. So if we don't tune our errors or our PIDs control, what we should be looking at is something like, probably like this. Like this. That's how it looks. Okay, it never goes down just because either it overshoots or it's underdamped. Okay, cool. I just wanted to let you know about what the error is. Okay, now let's talk a little bit about the PID. Okay, and then we go to program. Promise. Okay, what is a PID? Okay, so PID, let's see if it's good. Yeah, PID stands for PID stands for proportional, okay? Integral and derivative. Cool. So this is a PID controller, and all these three will describe how the error should be treated, okay? So these will work with the error. Not the actual input, but the error with the input, okay? Cool. Now, let's look at a little bit more of the numbers. Please don't freak out. Let's see how it looks. So we have the error here, okay? Error is fed to three things. 1, 2, and 3, okay? One is a constant, which is the proportional one. It's just a simple multiplication. Okay, it just multiplies by kp. Okay, the other one is a constant times 1 over s. Okay, 1 over s is an integral in Laplace transform. I won't explain what Laplace transform is. It's just an integral. Okay, and the derivative, it's the same constant multiplied by its own derivative. Okay, that's how it looks. Okay, it looks horrible, I know. I remember when I saw this the first time, it was horrible. It is, but it acts really cool. Okay, so just let's do this. Let's see, probably do this so we can use a little bit more space. How does this look? Okay, just quickly, proportional looks like this. Okay, so proportional will be blue. Okay, let's do integral will be white, and let's do this weird green would be the derivative. Okay, so the graph looks like this. So whenever we have like this, and we have our error here, and this is time. Okay, so for each second, let's say that the error goes like this. Okay, so we have, this is our error signal. What we will do with the proportional is multiply by each point. Okay, the bigger the error, the greater the multiplication. Okay, it means that if we have a lot of error and we multiply by 0.1, the error will never be 0. Okay, you might say, let's just multiply by 0. Yeah, but that will be just not using anything, because errors just don't go down to 0. Like mathematically they do, in real life they don't. Okay, so that's what they do. Integrals, what they do is based on the whole area of error, it will act upon the error. Okay, and derivatives just check, oh shoot, it was with green. Okay, they check every single point, they do a derivative. Okay, and depending on the slope, the PID will react. Okay, I know this is a lot. Okay, I just know this is a lot. It looks horrible. We'll get back to it, but let's go to the fun part. Let's kind of see how it works with ROS. Okay, cool. Let me just put my iPad here and get my computer. There we go. You might ask, what are you doing with your computer? Like, where's your computer if it's not here? Yeah, I have two. Okay, I have this one and this one, just because this one has Linux. ROS runs in Linux. Okay, just FYI, it runs on Ubuntu. Depending on the version, is the ROS version. Okay, cool. Let me just do this. I'll be sharing my entire screen. Cool. That should be visible. There we go. There we go. Yeah, looks horrible for now. Let's see. Cool. How does it look? Nice. Okay. Yeah, don't worry. Chrome just closed. Cool. Okay. So, quick recap from ROS. Okay. We have a terminal. I'll just open 4 terminals. I love 4 terminals just because it's easier with ROS. Okay. I'll zoom in here. Probably I'll zoom into this one more time. Cool. Okay. So, we're in Visual Studio Code now. Okay. This is what we did last time, and let's see now. Let's create something called turtle control.py. What? Shoot, turtle control. Let's do control.py. Okay, cool. Nice. Okay, so let me just open my helper script here. Give me a second. Let's see. There it is. Cool. Okay, so as always, the first thing that we have to do when we are writing Python with ROS is, there you go, as simple as that. Okay, We will import some messages. So from geometry messages dot message import should be pose, should be twist, and from turtle sim.msg import pose. Okay, I'll explain in a bit what that is. We need math and import time because we're going to derive it. Cool. Okay, so far so good. So we have ROS.py, which is what makes a bridge between Python and ROS. Okay, we have this thing, which is a message, XYZ message. You can send linear velocities and you can send angular velocities. Okay, we have turtle sim messages pose, which gives us the actual position of the turtle. Okay, so if you're wondering what turtle, if we go to, we have to do raw score here. Okay, so this starts the master node, and from here we do should be ROS run turtle sim node. There we go. That's a robot. Okay, it's a 2D robot, only moves in the X and the Y coordinates, not in Z. It can just rotate in its own axis. Okay, so this is what we'll be controlling, and from here we'll control a real robot in a simulator. Okay, cool. Just we'll remember some stuff. If you do, hey, how can I know if I can use these two? Then you just do this. ROS message. How was it? Messages list. ROS message list was better. Like, yeah, there we go. Cool. So we have all of these messages that we can use. But if we do a little bit of Linux here, we can do this, and then, okay, there we go. And then grep. We want twist. There we go. Here it is. Geometry messages twist. Okay, that's what we're going to use. Okay, same thing with pose. In this case, here it is. Geometry messages pose. Okay, that's what we're going to use. Cool. Now, let me just get rid of both of these. Clean my terminals because it looks kind of weird. There we go. Cool. Awesome. So when it comes to big projects or more complex projects in ROS, the best thing to do is create a class. Okay, using object-oriented programming with ROS is fairly simple. Same thing as with Python. So let's do class. Let's do turtle PID. Okay, cool. We have our init, thunder init, and we have self here. Cool. Okay, so first things first, we can have a ROS Python script, but it won't work if you don't have a node. Okay, again, let's just look at the notion here pretty quick. We have a master node, and for each node, we have something to control. Okay, so basically, we need a node for the turtle that connects to master. So that's what we're going to do. So let's do create node, okay, and we'll do ROS.py.init node, okay, and I don't know, let's do turtle PID, okay. That's how this node is called. You can call your nodes whatever you want, okay, and let's do anonymous equals false just to see how or what the name is, okay. Now, remember last time we said there are two types of nodes, publishers and listeners, okay? Publishers basically send the messages, listeners just listen to messages, okay? Cool, so let's do that. This thing won't be listening only, it will be publishing too. So let's start with publishers. So let's do self.publisher, just because we're going to use it in different parts of the class, equals ROS.py.publisher. Careful with that capital letter. We have to publish into the topic that our turtle can listen to. Okay, so let's just go here. If we rerun the turtle. Okay, so I'll just keep it up. Keep this here. Cool. If we do ROS topic list. Cool. Here it is. We will be talking to turtle1 cmdvel, which is the velocity command from the turtle. Okay. Cool. So let's just get rid of this, Control L here, here. Okay. Cool. So it was turtle1 / cmdvel. cmdvel. Okay. Why? Because we're going to publish commands to the turtle's command velocity. Okay. That's what we're going to do. Cool. And the next thing was, or the next question should be, what will be sent to this topic? We will be sending these types of messages, twist messages. Okay, so let's do twist here. And the next thing is queue size equals 10. Oh shoot, 10. There we go. Okay, queue size again is the amount of messages that will be stored up until the 10th in this case. Then we will start losing messages. Okay, so if you're sending images, it's probably best to keep the queue a little bit longer. Okay, so you don't like lose that much information. This actually doesn't really change anything in this case, just because the robot is in my computer, my master node is my computer, so there's no loss of information there. If you're working with a drone, then definitely kind of use a bigger queue size. Just careful with that because it uses RAM and it makes your robot a little bit slower. So if you need close to real-time responses or answers from your robot, then just make sure to have that queue size tuned up. Okay, cool. Now, and again, we are publishing or speaking to the robot, okay, but we kind of want to know what the turtle bot is. Okay, so let's just get back to our node here. We want to know where the position is because this is what's going to feed back to the reference. Okay, so that's what we're going to do now. So let's see. Cool. Now, subscriber. Let's subscribe. Subscriber equals ROS_pi.subscriber, and we will subscribe to another topic, which is /turtle1/pose. Okay, actually it's pose, right? Let's double check. Is it with capital letters? I know. There you go. If we do ROS topic list, it's not with capital letters. Okay, so we'll be subscribing to this position. Okay, nice. Let's just get rid of this. When you see reds in ROS, it's either a big bad error or just something so simple. Okay, errors in ROS are red. Okay, that's horrible. Cool. Because we'll be listening. The thing that we'll be listening is not a twist because it's not a velocity command. It's rather a pose message. Okay, listen to pose. And for each subscriber, if you remember last time, it's like your ears, okay? Just remember that. Again, you have your ears are connected to your brain, okay? They are active all times up until you receive a message, then they react, okay? Being active is not that they mean they react, okay? Because you're listening all the time to lots of things, the birds, cars, whatever. They are reactive at any time. But when you sleep, they're just active, but not reacting. Okay, so we want this to listen, and when something happens, it'll react. Okay, so we have to create a callback. Okay, so let's just self that pose callback. Okay, oh, shoot. There you go. Cool. Now for twist and for pose messages, we don't create them from zero or from scratch. Thankfully, ROS has created them. Okay, so what we want to do is just edit them. Okay, so instead of recreating them from scratch, we'll just get the message, rewrite them, and then send them. Okay, so this is what these two lines are for. Okay, self that pose equals pose. Okay, shoot. and self dot, oh yeah, actually, yeah, just pose, because the only thing that we're going to use is pose, and I'm pretty sure cmdvil to, yeah, let's double check that. Yep, I think it, yeah. I don't think we have to create a self dot cmdvil, just because we will just use it in one function. Okay, cool. Now, self dot rate equals ROS pi dot rate. Okay, and we'll give it 10 hertz. Okay, so the rate that you propose is the rate of you sending messages. Okay, 10 hertz means a tenth of a second. Okay, so each 0.1 seconds will be sending messages. Okay, and receiving messages. That's our communication speed. You might say, hey, why don't you just do it like super fast? Like, again, in theory, that would work. In practice, if you have a drone that's computing a lot of things, it won't go that fast. Okay, so 10 hertz is something like, for my own personal projects, I always use 10 hertz. Okay, I find it that it's like the best rate to use. Okay, cool. Now let's go into a little bit of a control systems here. PID paramps. Cool. So we will give some. Okay, so let's just get back to here, okay? Because if not, I'll confuse everyone. Cool. So remember this. We have this constant. We have this constant and the constant. Okay, so we have three different constants: the proportional, the integral, and the derivative. Okay, so we need three numbers that will stay constant the entire time. There are lots of ways of tuning and getting these constants. I did it for you. You don't have to do it. It's a totally different topic, complex topic. So we won't go into that. Just trust me with the numbers, okay? So if you do self-did KP, but there you go, linear equals 1.2. Yep, that was good. Self-did KI linear equals 0.02, and the derivative KD linear equals, oh, come on, there we go, equals 0.3. Okay, those are for the linears. Okay, so X, Y, those are linears. Okay, in this case, or I'll just explain that later, but again, remember, our robot is two-dimensional. It means it only moves in X and Y. It won't fly, so it doesn't go to Z. Okay, so linear means X and Y. Now angular, it means we'll change the angle from the Z position. Okay, so I don't know if you see my headphone or my earbud case, we'll do this, okay, which is rotating in our angle, and this is like the Z. Z is like this, so we'll do this basically. Okay, so we need some numbers there too, because if we say, okay, I want you to go back to 0.12 and it has to do like a circle, then it won't be able to do it without angular velocity. Okay, so we can do self-did KP angular equals 4.0. That was good. Self-did KI angular equals 0.01. Again, just trust me with these numbers. And self-did KD angular equals 0.5. Okay, trust me with those. And we have to store the errors. Okay, self-did previous error linear equals 0. Self-did previous error angular equals, let's do angular, equals 0. Okay, so the errors for now are 0, and self-did integral linear equals 0. The only errors that we are interested in feeding back, and I'll explain in a second, is the integral one. Integral linear equals 0. Oh shoot, it's not linear, it's angular here. Cool. Okay, so far so good. We just added some variables for us. Okay, cool. So let's do the post callback. Okay, the one that we should be using here. Okay, so what should we do when our ears, in this case, our subscriber activates? We will store the data that we get. Okay, the data will be the post. Okay, so I get the position, I store the position in one of my variable classes. Okay, I'm sorry, class variables. Simple. Okay, so def callback, was it called post callback? Okay, so self dot post callback self, and it should be, let's get the data here. Okay, always keeping Python good styling here. We'll just do callback that activates whenever we get data. Okay, cool. And we'll do self.pose equals data. Okay, basically this activates self.pose will become the value of data. Okay, cool. Now, what else? Now, remember our first idea. The first idea was I want my drone to go from point A to point B. Let's do the same with TurtleSim, okay? So let's do def move to goal. Cool, and we'll have, should be self, not Python gets mad. Let's do goal X and goal Y, okay? We will be interactively saying the robot, or telling the robot where to go, okay? So again, let's keep the styling good. Moves the turtle to desired X and Y coordinates. I don't like the word coordinates. Points. Yeah, that should be it. Cool. Okay, now, in theory, everything works. In practice, we cannot achieve perfection. Okay, that's a given. So inside of our errors, we need some kind of tolerance. Okay, so let's say I want to go from point A to point B. It's a straight line, and it's around 100 meters from point A to point B. Okay, so if I go to 101 meters, it's not that bad. Okay, I'm still in the range. Okay, so it depends on what you need. In this case, we will give it some tolerance, just because if not, it'll oscillate forever because perfection doesn't exist. Okay, cool. So let's do tolerance equals 0.1. There you go. Now, again, we have the self.pose here. Okay, we don't need to self it, so let's do twist msg equals twist. Okay, because it only will going to be used here. We are going to derivate. Okay, so we need time. So brief time equals time that time. Okay, so this gives us each time frame from each 0.1 seconds that we'll be deciding. Okay, and why 0.1 seconds? Because of our rate. Okay, so computation rate, communication rate, mostly everything will be computed at 0.1 seconds. Okay, again, if you want to do it faster, you can do it. Just make sure that you don't have any interference, nor your robot is speaking at a different speed than yours. Okay, cool. Okay, so as you remember, we have to do while not ROS pi that is a shutdown. There we go. Cool. Okay, this means while ROS is running, we'll do something. Okay, cool. First of all, we have to compute errors. Come on, compute errors. ROS errors. There you go. Cool. So we have to get error in the X, the Y, and the Z coordinates. Okay, so error in x equals basically our goal in x minus self.pose.x. How do I know this? Let's just get back to our notes. You can see here it says the error is the difference between the reference and the robot position. Okay, position is self.pose.x and our reference is the goal. Okay, fairly simple. Same thing with y. Error y equals goal y minus self.pose.y. Okay, fairly simple. Okay, same thing, no. For the distance, okay, we have to get a distance error. Okay, so x and y don't make up the whole distance. We have to do a Pythagoras theorem here, so we get the actual distance from one point to another. Okay, so we do math.sqrt, we do error in x squared plus error in y squared. Okay, that will give us the actual distance. Okay, so we just needed x and y to get the distance, and then we have to get the error of the distance. Okay, cool. Now, here comes some interesting math. Okay, now bear with me. We already have a distance. Okay, but as I mentioned before, our robot can only do as good as this and this. Okay, if we kind of want to go diagonally, we can go like this. Okay, we can go x and y and you'd get to the same point as if you were to go diagonally, but that's not the best option, is it? Because it just takes too much time. So we have to also work with angular velocity so that we, I don't know, if we want to go 45 degrees, we do this and then the robot just goes there. Okay, which is the best option. So we have to work with angles, okay? And ROS works in radians. It means from minus pi to pi, okay? That's how radians work, okay? Bear with me. If you're new to radians, pi is basically 180 degrees, okay? So it's from 0 to 360, okay? Basically saying from minus pi to pi, okay? That's how radians work, okay? Some more complex math, but let's just leave it there, okay? Cool. We have to get desired theta, okay? Desired theta is the angle that we want to go to when we are moving from point A to point B, okay? So desired theta is math.a102. This will compute the angles between the x and the y axis, okay? So it's error y, and error x. Cool. Okay, that's kind of what we want. And from this desired theta, we will check its error. Okay, again, it's a closed loop, so we need errors to feed back. Okay, so error theta, there we go, equals, actually it's desired theta minus self.pose. Okay, same thing as here. Okay, our goal is this desired theta. Our error is the desired theta minus the actual position of the robot. Okay, again, errors. Cool. Okay, now let's just do this. Why is the error from minus pi to pi? Cool. Okay, so in this case, we're just going to normalize this so it's easier. Oh, look at that. Let's do this. There we go. Equals, again, method tan2. And we do method sin of error theta in math.cos from error theta. Okay, for whoever is not familiar with this, we're just normalizing it from pi to pi with sine and cosines. Okay, sine is always X, cosine is always Y. Okay, cool. And yep, that's it. Cool. So we got the errors, we got the things that we need, which is the distance and the desired theta. Okay, now we know which angles we want. Okay, now let's compute PID. Okay, so first of all, because we are going to integrate and derivate, then we need timestamps. Okay, so basically we need to catch time frames and the time that will pass. Okay, so in this case, one of the algorithms is going to do this. Okay, the other algorithm is going to basically just get the area under this curve, and the other one is just going to multiply. Okay, the one that needs time is the derivative, which is the one that gets the slope. Okay, cool. So let's get time. So compute the time diff. Okay, so basically we need current time equals time to time. Remember, we have another time here, which is the previous time. Okay, so this time, this one right here is our reference, and we'll get errors based on that difference. Okay, cool. So current time equals time to time. dt, which is delta t, which is the difference of time, equals basically current time minus was it previous time? Previous time? Was it? Yeah, there it is. Okay, cool. And oh shoot, and now prev time equals current time. Okay, cool. So we're just calculating steps. Okay, each step from each time. Okay, cool. Now let's start with PID. Okay, so let's actually do this so it looks good. PID, there you go. Cool. So first part is linear velocity. Okay, so for linear velocity we have to integrate, multiply, which is a proportional, and derivative. Okay, so let's do this. Self that integral linear, which is this one. Okay, where is it? There it is. It's the error. Okay, the error in the integral part, in the linear part, which is x and y, will be something that sums up. Okay, and I'll explain it to you if we have time after the code. Okay, because it's a mathematical, let's call it bug. Okay, that you can integrate without doing lots of math. Okay, but just bear with me. Let's do error distance times dt. Okay, where do I get this? Why did I decide this? Simple as this. Here's the integral. It's our integral times our constant times the integral. Okay, this is in Laplace, so it looks chunky, but that's like, it's just basically integrating here. Okay, cool. Now times dt, and then it's derivative equals error distance minus self that prev error distance. Okay, over dt. Okay, for now this is how it looks, but this will be true if and only if dt, okay, if dt is greater than 0, else 0. Why this? Because if we divide over 0, we're screwed. Okay, there is no division over 0. Okay, nice. Okay, cool. Now let me just see. I think I just missed something here. No, it's fine. Okay, cool. Now we got the integral part, we got the derivative part. Now let's do let's send a message. Okay, so linear velocity equals basically self did KP linear times the error, okay? Plus, okay, why the plus? Because of this. Where is it? Here it is. Because of this plus. Okay, so we are feeding it back to our system. Okay, cool. Plus self dot ki, which is the integral linear, times, this looks horrible, times the error in, oh, sorry, this is not it. It's this one. Self did integral linear. Cool. This error here is this one. Okay, just because we have to keep track of our errors, then we have to plus equal here. Okay, that's why we save it. Okay, plus self.kd, which is the constant of derivative, times the derivative linear. Okay, which is this one. So error in derivative, I just missed it here. Linear, there we go. Error of derivative times our derivative error. Same thing with our integral. And basically the KP is just as simple as you see it here. It's just a constant. Okay, so it's a constant times the error. Okay, that's what we do here. Constant times the error. Cool. Hopefully that's not very confusing. Okay, and now let's just keep track of our errors. Self that previous error linear equals error distance. Okay, so this thing here, which is used here, will be used later. Okay, just we have to keep track of that. Cool. Okay, now everything that we did with the linear velocity, again, x and y coordinates, we'll do it with the z coordinate. Okay, which is angular velocity. Okay, so let's see how time. I'll do something that I don't like to do. I'll just copy paste the whole thing. And you'll say why? Because I'm running out of time and I kind of want to want you to see the other part, which is the AI part. Okay, instead of integral linear, this is angular. Okay, this is angular here. We do the same thing basically. Error. In this case, it's not error distance, it's error theta, okay? Because we're getting the error from the angle from the robot, okay? Derivative linear, it's not this, it should be angular here. It's not error distance, it's error theta, okay? Because we're not working with distance, but angle rather, okay? So let's prove error angular. This should be the same thing here. This is angular velocity. Okay. Each part that says linear, if you do Control D with Visual Studio, okay, you can select the same word without actually clicking on it. And we could do angular. See, that's great. Cool. Okay. Let me just double check that my error. This one's not good. Error theta, same as here. Again, we're not working in this part with linear, we're working with angular, okay? Cool. And now, it looks horrible, okay? I know, I get it. It just looks really messy, but it works. And let's see how it works, okay? The last thing that we have to do, we are publishing commands to the robot. The robot will listen to us, okay? So we have to publish them, okay? How do we do that? Let's see. Send commands. Cool. Nice. Okay, so twist message that linear that x, okay, equals, where does this come from? This comes from here, this part over here, okay? So I am modifying the twist message so that I can modify x value in linear, okay? Now, I'm pretty sure you'll get confused if you see this. Message, that angular, that's z. And you'll ask, Willie, why jumping straight to z? Why not going into y? robots don't usually work in the y coordinates, only z and x. Okay. In the end, if you have z, everything is x. Okay. So I just get my robot here. Okay. It's not the same doing this, okay, as doing this. Okay. You can actually do that. Okay. So you don't need actually y, because y it's up and down. So if you have z, you don't need y. You can just do whatever you want. Okay. So we'll just use the z part. Okay. So this is angular velocity. And then you ask, hey, what? Oh, shoot. Why did we need y here? Like the error y. Actually, if you see, the only thing that we used y for is to get the error distance. Okay. Because we need the reference. Okay. Oh, cool. Cool. Okay, and then self.velocity publisher. That publish will publish, okay, this twist message. Okay, whatever we computed, we'll be sending it to the turtle. Let me just double check we have this existing. It was self publisher. Okay, self.publisher. Okay, cool. Let me just double check if my code's correct. Let's see, it should be, yeah, it should be. Okay, cool. Now, let's see, it's here. Okay, cool. Now, let's do something more visual, which is log info, okay, which is, it's like a print statement for ROS, but that doesn't actually interfere with the ROS, okay? Let's do an f string moving into, or actually two. Let's do this. It's goal x, goal y. Okay. Cool. I think that's it. Nice. Okay. So it's moving. We are sending moving commands, but we will never, or we haven't said, hey, you found it, stop. Now let's stop. Remember that we had a threshold of error, okay? Cool. So error distance is less than, oh shoot. And then, okay, so if we are 0.1 away from our goal, it's still acceptable to us. Okay, so let's just stop there. Okay, ROS.py did log info. We got there. Okay, and twist message did linear.x equals 0. Twist message dot angular did z equals 0. Why not y? Because we're not moving in y. Okay, just remember that. Cool. And now self.velocity. It's not velocity though, it's publisher. That publish twist MSG. Okay, so now we're sending a stop message. Okay, cool. Now we always have to do this. Self dot rate dot sleep. What this means is we will go 0.1 seconds for each computation. Okay, if we don't do this part, ROS will just get messy because we speak, in this case, probably won't, but if you're speaking to a real drone that's flying, you have to wait for the signal to go into the drone to compute, and signal to go back. Even though it's pretty fast, it takes time and it desynchronizes with your computer. Okay, so you'll get images. If you're getting images from the drone, you'll get images from the past. Okay, so you'll compute in the past. Okay, so you have to tune that up. Just careful with that. Okay, so we have to do the sleep here. Whew. Some water. class is over. Okay. If name double equals run domain. Okay. Always keep Python best practices. We'll do turtle C controller equals turtle PID. Was it PID? I'm not sure. Let's see. Ah, here it is. Turtle PID. Okay. Cool. So turtle PID. And now we have to get the X and the Y coordinates that we want the turtle to go. Okay, so X goal equals, it should be a float, okay? It's an input of what's the X? Desired X. Probably let's do this. Cool. Same thing with Y, okay? I'll just copy paste the whole thing just so we reuse some code. Y goal, what's the desired Y? Okay. And now turtle controller dot move to goal, X goal, and Y goal. Cool. Let me just double check that. Oh, goal. There we go. Turtle PID with the with more P. There we go. That should be it. Okay, let's test it out. Move to goal. Let me just double check if I have the same name. Yes. Okay. Ready for the errors. I'm pretty sure we'll have errors. Okay. Let's go to terminal. Okay. Now start the simulator. Do I have it here? Yes. Okay. Cool. So cross the fingers, and ROS core, which is master node for ROS, it's on. Let's do ROS run, turtle sim node, open the turtle simulator. We have our simulator robot here. Let's hope that works. Python 3, turtle control. Okay. It wasn't this one. Shoot. Was it Q? I'm not sure. Yeah, there it is. Sorry about that. It was control. Turtle control was the last time's control. Okay, what is desired X? Let's do 2. What is your desired Y? Okay, in this, by the way, in this like ocean. I don't know. Let's do 3. Ah, there we go. Errors. Okay, let's just fix that. Brief error distance. Gates line 71. Let's double check that pretty quick. I'll just close this. That's okay. 71. Solve brief error distance. Okay. Self the brief error distance. What was it then? Self the. Give me a second. Self the previous error distance. I didn't actually use this, right? Ah. Okay. Was it this one? Why did I add a self here? Not sure. Brief error. Wait a second. Where's the previous one? Did I just miss it completely? What? Okay. Let me think, because they're linear. Ah. Isn't it linear here? Yeah, why did I do distance? It's linear. Linear. Cool. That should exist. Yeah, it exists there. Ah, there we go. This linear, angular. Cool. Now, sorry about that. It always happens. Let's do always on top. Rerun it again. Desired X was 2. Desired Y was 3, was it? Yep, there it is. Okay. I'm not liking that. Okay. We got there. Okay, cool. So what happened here? Remember I told you there is no perfection? This is not perfection, okay? This is a controlled system that oscillating, okay? And you can see it here. We got there. Actually, not oscillating. Wait a second. Wait a second. That's my fault. Sorry, turtle. Sorry, turtle. Okay, yeah, I know why I did that. Okay, so that's how oscillation works, okay? It never gets to the point, so it always feeds back more and more and more, and it just oscillates forever, okay? Now, just get rid of this. It was a simple mistake. What was it, you may ask? Yeah, we never got out of the loop. Okay, cool. Now this terminal just died. Thank you so much. Let's do cd catkin src. Was it streams intro to ROS? Yeah, there you go. Now Python 3 again. Let's do this one more time. Third time's the charm. That's what they always say. Python 3. What was it? Control? Okay, cool. Desired X. Let's do another number. 2 was there, so let's do like 4. I hope I don't get out of bounds. There we go. That's 4, 6. We got there. Okay? Isn't that cool? Okay, let's do another number, okay? Let's do... Is that 4, 6? I'll do 9. I hope I don't get out of bounds. And 1 in Y. Oh, there it is. Cool. Now, the robot is just moving by itself. Okay. We're just saying, hey, I want you to actually, let's see. Let's do something because this is too noisy for me. ROSPy.log info. Let me just get rid of this. Cool. It's just too noisy for me. Cool. Let's do this again. Let's go to same thing, but like 9 and 9 should be, there it is. Okay, no need to use Y. Okay, it says, so cool, what have you, okay, that's a very interesting question. What happens if you type a location that's out of bounds? Let's do that. Okay, the turtle will just freak out. Okay, I think 9, 10, probably 15 should be out of bounds. Okay, yeah, that's what happens. Yeah, you see, it says here, oh no, I hit the wall. Okay, and the bad thing about this is that because the control system is trying to get to that point, it'll never go there because it's out of bounds, so this will never stop. That's a bad thing, okay? So we have to put more tests, like, hey, if it's more than 10, just ROSPy, the log info, that's out of bounds. We cannot go there, break, okay? That's how it should be, like, done, okay? Cool. Nice question. If I do Control-C here, it won't break. It broke, cool. Let's do 1, 1. There we go, cool. Now, that's stationary again. Now, I kind of want to try this with the turtle sim. I'm sorry, the turtle bot, which is the robot that we used last time. Fair warning, let's do it. I don't know if it works. Okay, I didn't try this before the stream. I just thought of it now. Let's see if that works. Okay, cool. So, and this will serve as a quick refresh, okay, about last time. Cool. So, if you remember last time, we needed to go here. Turtle ball 3 manual. There we go. Simulation. Okay, cool. Now, this is a robot that's a third-party robot from Robotis. Okay, you can simulate this. Okay, we simulated it last time because it's a third party. It's already done. So we just have to follow this. So let's do, we have to get rid of this, by the way. So Shift Control V, and then we get to this. I don't know if it'll work, huh? I hope it works because it'll be really cool. Okay, nice. It's starting the simulation. You can do it, computer. You can do it. There we go. There it is. Okay, cool. Now, there's the robot, okay? Now, this is like the turtle bot, okay? It's like the turtle sim. It's an X and Y linear robot. It doesn't go up in Z, okay? It doesn't fly. So if it were to be a drone, we would have to do a linear Z calculation too, okay? But because we don't have that Z part, it acts as the turtle sim. It's like a car. You cannot fly with a car. You just go straight and you can just turn around, okay? But don't fly, okay? Cool. So let me just do this probably, then do this. Let's see it from here, okay? Can you see it? Is that okay? Cool. I'll probably just zoom in a bit. I said a bit. There. Come on, just a teeny tiny bit. It's too. There we go. Cool. No, I'll just keep it as it was. Okay, like this. Cool. So you can see it. It's a small black dot. That's our turtle bot. Okay. Now we have to change some things. Okay. With this robot, we have to do ROS topic lists. Okay, because this robot doesn't have the same topics, or probably doesn't have the same topics as the last robot. Okay, so hopefully, see, this one has CMDVal, but in our previous one, we had Turtle One CMDVal. So we won't be using this one. Okay, I suppose same as this. Okay, let's see if we have pose. Great, we don't have pose. I think I have to use odometry. Yeah, this won't work. Now that's bad. Okay, yeah, that's really bad. Can I use odometry? I'm not sure. I don't want to waste any more time. I kind of want to go to the AI part. Just for fun, okay? Grip, pose. Yep, no, we don't have pose, okay? So it could be done, okay, using odometry, but you have to tweak a little bit more things. You know, it could take like 10 to 15 minutes just to figure this out. I don't want to use that time. I kind of just want to go into controlling a robot with your hand, okay? So let's just skip that part. I thought we could do it, but we can't, okay? Cool, again, let's just see it one more time because I kind of love it. Okay, cool. Now this is Control C. Control C, come on. I have to force this probably because Gazebo always takes a little bit more time, but yeah. While it's closing, okay, cool. Just crashed, nice. We do raw score here. Okay, thank you, sir. What happened is we had two raw scores running and that cannot happen. Again, let's do ROS run, turtle sim, node, cool. Let's just do this one more time because I really love to see it. Okay, let's do 3, 9. Great. What? Nice. Yeah, I know what happened. We just moved this slash turtle 1. See, even though the code is correct, we are not speaking at the same channel. Okay, let's do 9, 5. Ooh, there you go. That was a laggy thing. There you go. Nice, cool. Okay, it worked. Yay. Okay. Nice. Control C this, Control C this, Control C this. Okay, cool. Now, let's just get rid of these, and these. Okay. So the next part is an interesting part. Okay. Now you saw how control systems work. Okay. Again, just 2 minutes of recap. It's a closed loop. We get the position. You can either proportionally, integratively, or derivatively calculate the error. From the error, you send it to control, and then you send it to your plant. Your plant is your robot, okay? Your drone, your car, your, I don't know, your robotic arm, whatever, that's what control does, okay? It kind of looks a little bit like reinforcement learning, which is not the same, okay? One is a deep learning part, the other one is just control systems, okay? But this is what's used in lots of factories, in lots of autonomous systems before going into AI, always try to see if you can, with control systems, if you can solve it, the problem. Okay, cool. Now. No. Okay, cool. So no neural networks whatsoever. Okay. Now, we will not write neural networks from scratch. I think some of you had the workshop with Steven last time. What I'm going to do is, with a camera, with a media pipe neural network, use my hand, okay, to control a robot. Okay, let's do it. Okay, let's see if we can do it in 30 minutes. Okay, so new script. Let's do camera.py, and let's do another one called turtle.py. Okay, let's just write turtle first because it's the easiest. It's fairly simple. Okay, cool. So as always, import ROS.py. Okay, now let's see. Same thing. Okay, because we will be actually sending the robot twist messages, which are moving messages, and we'll be getting strings. Okay, we'll talk between two nodes with strings and the turtle but node with twist. Okay, cool. So let's do from geometry message import twist. What? Import ROS.py? Why is this weird? Let's see. Turtle.py. Oh, that's kind of weird. Why is it all weird out? Just do this. No, it's fine. What? Okay, I don't know. Cool. Okay, and from std messages, the message, import string. This is just weird. What? Control X. Print hello. What? If I do it here, would that happen? No. What? Is it because it's called turtle? I'm not sure. I'll just get rid of this one. This is a weird thing. Yeah, much trash. And let's see. Turtle2.py. Okay. Should work. Works. Okay, I don't know what happened there. Okay. Cool. Now again, with projects in ROS, always try to use classes. So let's do class camera turtle. Okay. Let's do init self. Okay. We don't need any more. We need to first, as always, create a node. Okay, so init node. If we don't do a node, we cannot do anything in ROS. Okay, so ROS.py.init node. Let's do, I don't know, turtle node. Let's do anonymous equals false because we want to see it. Cool. Now let's subscribe. Subscribers. Okay, so the camera, which is the camera node that we'll be writing in a few seconds, is ROS.py.subscriber. Probably cam info. Okay. We'll be getting strings from the camera. Okay, and as always, with something that we listen or hear, we need a callback. Okay, so callback. Back. Okay, there you go. Cool. And self.camera string, camera feed equals string. Okay, so we'll be using this too. Okay, for publishers, we'll do self.control. Probably, yeah, let's do self.control. Self.control equals ROS.py that publish. Let's do, so it's for turtle sim. Okay, so we do /turtle1/cmd val. Okay, we have to send here a twist message. Okay, queue size. Okay, there we go. Now just get the rate. Okay, self that rate equals ROS by that rate. Was it with? Yeah. Okay, cool. And yeah, there you go. So next thing that we have to do is callback function. Okay, self best practices callback for when we get data. Okay, cool. So self.camera feed equals feed the data. Okay, so why did I do this? Just because I don't want any nones in my code. Okay, because if not, then you just get a horrible error that says cannot work with non-time type. Okay, just if you don't want to mess with that, just just create your variables. Okay, should be actually self feed the data. Okay, cool. Camera feed. Actually, we should get this. There you go. Cool. Now, I'll probably won't do the shutdown. Let's see what happens. Okay, def move and self. Okay, now this is an important step. Okay, so function that makes the turtle move. So we have three types of input. Okay, we have left, which will be 0. Okay, forward. Oh, come on, FWD, which should be 2, and backward, which should be 3. There you go. Cool. Now, first of all, let's init the command, which is move cmd, which is the message that we'll be sending. Okay. While ROSPy is still running, okay, that is shut down. Okay. Let's see. If, okay, self.camera feed double equals left. Okay, that's what we'll be sending. From the other code, we'll be sending a left string. Okay, so if we get a left string, this means, hey, Mr. Robot, please go that angular that z equals 0.5. Okay, it means rotate 0.5 in your z in angular velocity. Okay, let's do, well, yeah, let's not do prints. Okay, elif self.camera feed double equals was it forward, then move cmd that should be linear dot x equals 0.5. okay, for forward, and we'll do the same thing but for backward. Okay, Control C, Control V. Okay, this is backward. Okay, and this should be minus. Okay, cool. And let's publish the message. Okay, so let's use self.cmd control that publish move cmd. Okay, so from our publisher, which is this one, it's not cmd control, it's control. Self.control, we publish move command. Okay, cool. Now self.rate.sleep. Cool. So if you don't do self.rate.sleep, again, computer just goes at 1 hertz. It goes at 1,000 hertz. Okay, it can go at the rate that it wants, and we want to have that controlled. Okay, so careful with that. Cool. Okay, so we finished with this code. So if name double equals under main, let's do camera. Let's get this here. Control C, Control V. Let's do it a little bit faster. Dot move. There you go. Cool. Okay. So basically, this Python script gets from the other script that we'll be writing now commands and just sends them to the turtle, okay? And you'll ask, hey, okay, so if we have two scripts, what's the, like, why would you have two scripts? Like, why not one? If something fails, you don't have two, or like one big script, okay? It's better to do one node that does one specific thing, talks to another node that does only one specific thing. In this case, our camera will do the AI part. We will get the message, send the message to another node, and the node will be the one that sends the message and controls the robot, okay? For debugging, that's the best way to do it, okay? That's why. Cool, let's go to camera, okay? So let me get the code. This is a very long code, so let's type fast. Oof, like 150 lines. Okay, water. When you talk this much is, you definitely need water. Import CD2. Media pipe. SMP. Media pipe. This lets me know that I have to have an environment. Okay, cool. Import ROS pipe. And import from std messages, that message, import string. Okay, very simple. We will be using strings to communicate from one node to another. Okay, cool. Is media pipe correct? Media pipe. Yes, there is. Okay, cool. So class lets you hand tracker. Okay, cool. Now, def init. This one has a lot. Okay, so cool. Mode equals false, and I'll explain each and every single one of these in a second. The max hands, I put it in 2 just because if it doesn't actually see my hand, it has a margin of error. Okay. Detection confidence, I'll do 0.5. Okay, I'll explain this in a second. Let me type model complexity equals 1 and track confidence equals 0.5. Okay, cool. So mode in false, it's dynamic. Okay, if it's true, it'll be static. It's just a picture. Okay, if it's in false, it's dynamic, so I can move my hands to the camera, which is here, and it'll track as a video. Okay, max hand is the maximum amount of hands that MediaPipe will be able to see. In this case, 2. Okay, I'll just put 2 just in case I pass my hand, there are no errors. Okay, the detection confidence, it goes from 0 to 1. The more confidence you give it, the more computational power you need. Okay, I put 0.5 because it works. Okay. Model complexity goes from 0 to 2. At the 0.5 detection confidence, I just put the middle part just so you know I don't use that much power from my computer. And the track confidence, same thing. It keeps track of the hands. Okay, cool. Okay, nice. Let's do publish. Let's do first init node. So init node. So ROS.py. That init node. Let's do camera node. Okay. Let's see here. Was it? Let's see. Turtle mode. Yeah. Camera node is good. And anonymous equals false because we're going to use it. Cool. Okay. Publishers. Cool. So we do self.pub equals ROS.py that publisher. My typing is getting slower each time. Camera. Okay, we have to publish into the same topic. Okay, the topic that we're going to use is cam info. Okay, remember in a few minutes ago we tried to publish into another topic the same message and the robot didn't listen to us. Okay, so careful with that. Camera info, it should be a string because we'll be sending strings, and the queue size equals 10. Okay, cool. And I think that's it. Yeah, we have to do rates. Self rate equals ROS.py that rate, which is 10 hertz, which is good, each 0.1 seconds. Okay, now's a lot of typing part. Okay, so this is all media pipe code. Okay, cool. So we do self-did mode equals mode self-did max hands equal max hands self-did detection confidence equals detection con self-did model complexity equals model complexity. There you go. Self-did track confidence equals track con. Okay. Self-did MP hands. What? Track. What? Why is this an error? Self-did track con was track con. What? Okay. What? What? Why is there an error here? Oh, wait a second. What is this called? Why? Oh. It's thunder. What? Wait a second. Am I missing a comma or something? Ah, here it is. I knew it. Always happens. Cool. Okay. Self dot mo it's MP hands equals media pipe dot solutions dot hands. Okay, this is the neural network that we'll be using. Okay. Self dot hands equals self dot MP hands dot hands. Okay, and in this case should be self-did mode, self-did max hands, self-did model complexity. Okay, so we're just starting the neural network. Complexity, it's written, yeah. Self-did detection con. Self-did track confidence, track con. Okay, there you go. Cool. And now self-did MP draw. If we want to draw the hands, equals MP dot solutions dot drawing utils. Okay, utils. There you go. That should be it. Woof. Okay, that was a lot of code. We have like this is like 1/4 of the code. Okay, we have a half an hour. Let's do this fast. Okay, let's find the hands. Okay, now we have a neural network that will read the image and it'll find the hands. It's already tuned. We do not have to fine tune it though. It's ready to use. Okay, let's go there. So def and finder. This is a lot of media pipe code. Image and we will draw it equals. Cool. Okay, this basically, let's just prettify this a little bit. Finds the hands in land and places landmarks. Okay, cool. Now the landmarks are. I'm going to show you what landmarks are in a second. Okay. Let's see. Image RGB equals CV2 dot convert color image. Okay, from image to CV2 dot color BGR to RGB. Okay, why should I do this? Color, is it correct? Yeah. Okay, what does BGR to RGB mean? It means we are getting the image from the camera, but it's in BGR format. It means it's in blue, green and red. Okay, BGR. If we want to do RGB. Okay, so OpenCV just does it for us. Okay, cool. If we don't use it, then it's going to strike an error because it won't read correctly. Okay, reds will be blues, and that's not a good idea. Okay, self-did results equals self-did hands that process. So we process the hands, the image RGB. Okay, RGB. There we go. So we have the neural network. We process the image, And let's see if we have some hands. So if self that results that multi hand landmarks, and what does hand landmarks mean? Okay, that's a great question. Media pipe hand numbers. Okay, it's this one. Cool. Here we have it. There it is. Okay, can you see that? So red dots are landmarks. Okay, so whenever I'll put my hand in front of the camera, it'll create landmarks in my joints. Okay, so each one per each join, 1, 2, 3. Yeah, like we'll have a lot of more landmarks than joints, but those are the landmarks. Okay, so we can control them. We can do this, and we can measure the distance from one to another, and then control from that. Okay, so forward will be like this, backward will be like this, and right or left will be like this. Okay, that's what we're going to do. Okay, cool. So let's see if we have landmarks. Okay, thank you, Google. Let's see. That's it for landmark and self.result. Actually, this. Let's just copy paste because I'm running out of time. There we go. Then, if we want to draw it, then self.mp, which is media pipe draw landmarks. I'll get the image, I'll draw it in the image, I'll draw the landmarks. Self.mp hand connections. Okay, so what we're going to do is actually draw this in my hand. Okay, cool. And we will return image. Wait a second, it's not image. Yeah, we should return the image. Cool. Okay, so woof. Okay, have the code. Let's go. The position finder. Okay, so let's see, image and no equals 0. The first hand only, draw equals true. Okay, so this means we'll get the image, only we'll get the first hand. Okay, if the camera gets to see 2 of my hands, it'll just focus into 1. Okay, even though it's looking at 2. Okay, and true. Okay, cool. Now quickly let's do finds the position of the hands and gets the position of the fingers. Cool. Okay, so this wouldn't work if we don't have a hand. Okay, so just in case we don't have a hand, if self.results multi hand landmarks. So if we don't have this, don't do anything, basically. Okay, cool. Let's do hand equals self.results. It's actually this. In marks in hand. No, okay. Basically, we'll get just the first hand. Okay, cool. And let's see. For each ID, because we'll have an ID, and you can see the ID here for each number and landmark. And enumerate hand landmark. Okay, so for each hand landmark that we have, okay, we have height, width and color equals image.shape, just in case, and cx, which is in the x value, in the y value, equals the integer of landmark in x times, times width. Okay, what we're doing is we're placing the landmarks inside of the image, okay, because it's not the same as having the landmarks as placing them inside of the image with certain width and height. Okay, int landmark dot y and times h. Okay, same thing with the y part. Cool. Self dot landmark list dot append, and we'll append a list with the ID of the landmark, cx and cy. Okay, we will just append this to know where each landmark is inside of the image or relative to the image. Okay, cool. Now if id double equals 0 and draw, and I'll show you why, draw, then we'll draw the circle in the image. We'll draw a circle, a magenta circle. Okay, image in cx, cy. Size 10, color is going to be 255 in reds, 0 in greens, and 255 in blues. Okay, why is that? Because I want to draw number 0, which is my reference. Okay, so it's in the palm of my hand. It will be here. So I can measure from the tip of my finger to the palm of my hand, each movement of my hand. Okay, cool. Now, and I have to fill it. So cv2.fill. Okay, cool. Now, cool. That's great. Now let's go to the next one. We'll get the fingers that are down. Okay, equals this. Shoot. There you go. Cool. Okay, so we will get a list of fingers that are down, and I'll show you how. Okay, this will return if fingers are down relative to the palm, which is 0. Okay, so if a finger is down relative to the palm, give it to me because I want to know which one is it. Okay, so let's do. We'll have each finger has its own height, and we have to be careful with that because relative to the palm, one of the fingers is going to be higher than the others, and it doesn't mean that it's down. Okay, so if I'm doing, I don't know, this, it's down, but if I do this relative to this finger, the y, this is shorter, and it will mark it as if it was down. Okay, so just with each finger we have to be careful. Okay, and let's see, equals an empty list. Okay, for finger in fingers. Okay, if finger double equals 4, then let's see, heights did append true if the absolute value of self.lm list in finger in 2. Okay, the 2, this one here, it's the y value. Okay, so we're not interested in the x value, but in the y value. Okay, so we'll see if the fingers are down. Okay, minus self.lm list, same thing here, 0 and 2. Okay, and this should be less than 100. Okay, cool. Now this is a lot. Let's just see what Yes, false. Why am I missing a the absolute? This is not correct. There. Yeah, there we go. Cool. And false is with a capital F. There you go. So we want to see if finger number 4, which is this one, okay, the thumb is up, and for me personally, the value has to be greater than 100, from 100 up. Okay, so that's like the size in pixels for my thumb. It depends on your thumb, okay? But for my thumb, it's 10 pixels. I'm sorry, 100 pixels. So yeah, okay, cool. I'll just speed this up because Jocelyn has a great stream for you, and I kind of don't want to take too much of her time. So else heights to the pen, true if the absolute value, kind of the same thing, right? Kind of the same thing of this. Okay. This should be 90, and I'll explain in a second why. Finger. Okay, cool. So now I'm getting my highest finger, or the finger that I'll be using the most, is this one, okay, the thumb. So relative to the thumb, I want to control everything, okay? If it's the thumb, because this is the shortest one, I want to do 100. If it's above 100, it's up, okay? If it's less than 90 and it's not the thumb, it means the other, or one of the other fingers are down, okay? And I'll just return here the heights. Okay, cool. How much code am I missing? Oh shoot, this is a lot. Okay, cool. So if I type, I'll take more time. So let me do something that I kind of didn't want to, but I'll have to, okay? Cool, let's do this. Nice, okay, so I won't have time to finish that code, okay? It was a lot of code. Ooh, that looks, there you go. Is that better? Nah, that's better. Okay, cool. So this is the same code that we were actually writing. Okay, here you can see model complexity, position finder, same things, okay? This is the function that we were writing, okay? Let me just explain to you the functions and how they work, and then we'll test it, okay? Here it says the gesture command. So I want to see if the fingers down are 20, 16, 12, and 4. It means I want to see if 20, 16, 12, and 4 are down. It means I'm doing this. Okay, if it's this, then please send a forward message. Okay, same thing here. If my finger down is fingers 8, 12, 16, and 20, 8, 12, 16, and 20, it means I'm doing this, not this, but this. It means go backwards, okay? Forward, backward, okay? Lastly, if it's fingers 8, 16, 12, and 4 that are down, 8, 16, 12, and 4, it means just the pinky is up, then it rotates, okay? That's basically it. Here is just code of capturing the video, okay? Hand tracker, okay? And basically just capture the video, okay? That's the same thing, okay? The move turtle is the same. We're doing the same, okay? Forward, left, and backward. Cool. Okay. Let's test it out. Let's see how this works. Let's start ROS core one more time. And let us start with ROS run turtle sim node. Okay, cool. There's our little turtle. This one looks like Blastoise. By the way, FYI, each turtle or ROS's versions are like turtles. Okay, so Noetic's version, which is my version, I think it's like a Ninja Turtle, which is green. If you run a lot of times turtle sim, you can find like a lot of turtles, and each turtle is a ROS version. Okay, just FYI. Okay, cool. Now, let's do this. So, because I'm using MediaPipe, I kind of want to use my virtual environment in Python. If you don't know how to start a virtual environment in Python in Linux, you do Python 3-m VNV, and I like to leave it always env. Okay, so Python 3-m venv env. Okay, in my case I just have it. You can see it's there. It's env. Okay, so let's do source env bin inactivate. It's activated. You can see an env here. Okay, now actually now that I see this, I need to another terminal. Okay, cool. Cd catkin src streams turtles in hand control, same thing, source env bin inactivate. Cool, nice. Now I'll just do this now. Okay, so first things first, open my camera, python 3 camera.py. You'll see two versions of me. There you go, that's me. Hello. Cool, you can see my hand, right? Can you see that? Can you see how it's, see the landmarks there? See that they are red, and I have a like a pinkish landmark here, which is my palm. This is my my reference. Okay, cool. Now let me just do this. Okay, put turtles in here and this one here. Okay, last thing. What was it? Python 3 camera? No, it was turtle control. Shoot, what was the name of this? Move turtle. Okay, Python 3 move turtle. Cool. Now that's listening. You can see that the data is nothing. Okay, backward. Okay, cool. That's weird. 3, 2, 1. Forward. Okay, there's my camera. It's going forward. Pinky is for rotation. Pinky. I said pinky. Left. There you go. There you go. Let's go. Why is it? Is it like the position of my hand? There we go. That's probably it. There we go. Turning left, 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 left. Let's go backwards. 3, 2, 1. There it is. That's cool, huh? And now let's, if we use our other finger, there we go. Move forwards. Let me rotate a little bit. There we go. Move forward there. No, I said forward. There we go. Cool. Now, I guess I have to have like my hand really steady, so for it to really compute. There you go. And that's AI, okay? That's the difference of AI and control systems. Okay, I'll just stop my camera right now. Cool. The difference between control systems and AI is that one needs neural networks, the other one doesn't. Okay, it might seem that both of them are kind of the same thing, okay, but they're not. Okay, one doesn't use that mod computation power, but it could be a little bit more complex to do. And it depends. You cannot use a camera, you cannot use other stuff in control systems. It's just basic math. For a neural network, it's easier because you can use neural networks. You can use a camera, sensors. You can pre-train them with whatever you want. And that's the cool part about it, okay? It's up to you to decide. Cool, okay, let me put the computer here and share with you. Where's my, there it is. Okay, cool. So please, please, please go get your points from this link over here. Nice. And Jocelyn, which is coming up, will present to you, create your first recommendation system, okay, in 5 minutes. Okay, so thank you all for joining. Jocelyn, I'll leave it up to you. I know she's listening. So good luck with Joss. Have fun. And don't forget about your points there. Hey, thank you so much. Thank you for being here. And if anything, let me know on Discord and I'll be able to help with you with ROS. Okay, thank you all. Bye-bye.